Today, we want to talk about some more constrained optimization, and we're going to talk about the Lagrangian function. If you were to recall, when we're trying to optimize a function, say f of xy, and we're subject to some constraint, g of xy equals a constant, we want to set up a system of equations to solve. And that system of equations will be the gradient of f equals lambda times the gradient of g. And g of xy equals some constant, the constraint. Notice that the gradient function does not care about the c. We just want the gradients to be pointing in the same direction. I want the gradient of f and the gradient of g to be pointing in the same direction. Also notice that we have three variables running around. We have x, y, and then we've introduced another variable lambda. That's the Lagrange multiplier. We've introduced another variable lambda. And notice that we've set up a system of three equations. The gradient of f equals lambda times the gradient of g will have an I component and a j component that are going to be equal. And here's our third equation, which is just the constraint. One way we can summarize the system of equations is to set up what's called the Lagrangian function. So the Lagrangian function is going to be f at xy, our objective function, minus lambda times our constraint as a function. So g of xy minus c. And we're subtracting these two so that when we take the derivative, it comes from these two things being equal when we take the derivative. There's the short answer. So notice that this really comes from f of xy equals lambda times g of xy. And then imagine putting those two things on one side of the equation. Taking gradient of f equals lambda times the gradient of g, putting it on one side, saying gradient of f minus lambda times the gradient of g equals 0. And then imagine doing that with this constraint function, g of xy minus c. That comes from g of xy equals c and subtracting c from both sides and making one expression out of it. So in the Lagrangian function, we just need to take our first partial derivatives, set them equal to 0, and solve. Done our classic maneuver in math, where we take the current problem that we have and reduce it to an old problem. Oh, you want to optimize? Take the derivative, set it equal to 0, and solve. Oh, you have a system of equations, make one function, take the derivative, set it equal to 0, and solve. So here's one way to just combine the objective function and the constraint function together into one function. We'll take the derivative, the three partial derivatives, set them equal to 0, and solve. So we need a function. And so I randomly generated a function that has nothing to do with an email about chapter 15, section 3, question 4. Nothing to do with that email. It just might happen to look like that. So in this problem, we want to maximize this function p of x subject to this constraint. So my g of x will be 38.5 x plus 35y equals 1.6 million. So here's our g of x is 38.5 x plus 35y. Or sorry, our g of xy is 38.5 x plus 35y. So for those of you who have done or are going to be working, actually for all of you, it's the same thing. The problem setup is that we have $1.6 million to buy rice and beans, X bags of rice and Y bags of beans. So what this equation is telling us, here's our $1.6 million budget. That's our constraint. And here we are buying X sacks of rice at $38.50 per sack and Y sacks of beans at $35 per sack. So that's where this function comes up. This is our constraint. Our constraint is money. One of the big problems with doing these kinds of problems in math classes, a constraint is always about money, and a constraint is usually in the real world less about money and more about political will. So if we could find some way to quantify that and drop that into equation instead of money, then we might be onto something. But we always use money, which is kind of weak. P of xy is supposed to represent the number of people that we can feed with these X bags of rice and Y bags of beans. So 1.1 times the number of bags of rice plus Y times the number of bags of beans minus XY over 10 to the 8th. So this is probably some kind of factor or term that has to do with us distributing all this stuff. I don't know where the equation came from. I can just read what the equation is doing. So once again, I can't totally explain what the equation came from, but this is what the equation is doing. I could think about what the numbers do in the equation, but we don't need to, because our objective is to math things, not feed people. This is America. All right. So let's set up our Lagrangian function, take our partial derivatives, and set them equal to 0 and solve. So our Lagrangian function for this example we're going to have f of xy, our objective, minus lambda times g of xy minus c. So I'm writing this as a function and just putting the 1.6 million on the other side, subtracting it from both sides. So it's going to be the minus c. Minus lambda times 38.5x plus 35y minus 1.6 times 10 to the 6. So here's our Lagrangian function. Tell it's a math person doing this problem because 38.5 and 35, and then the 1.6. How are you deciding how many significant figures you're using? And it's just, the answer is just kind of shrug. And then you're like, well, why didn't you just call the 38 39? So let's find the partial derivatives with respect to x, partial derivative of L with respect to x, y, and lambda. Scroll. There we go. So the partial derivative of L with respect to x, we're going to have 1.1. The derivative of y with respect to x is just 0 because y is a constant term. The derivative from the x is the variable in xy over 10 to the 8th. Y over 10 to the 8th is all constant. So we'll have minus y over 10 to the 8th. I'm going to turn this all into terms. This is all going to be minus 38.5 lambda x minus 35 lambda y. And then minus and minus is going to be plus. We're taking derivatives, so that's not going to make much difference. Minus minus is plus 1.6 times 10 to the 6th lambda. I'm not sure how many signs you drop when you do these problems, but I drop this sign all the time because I forget the minus. So I need to write it out. So we're taking the derivative with respect to x. We'll have minus 38.5 lambda, because that's all constants. The next term is has no x in it, so it's a constant term with respect to x, and the last term is constant with respect to x. So there's our partial with respect to x. Now we need our partial with respect to y, so we'll do similar things. So we're going to have 1 minus x over 10 to the 8th minus 35 lambda since the x term is constant with respect to y, the lambda term is constant with respect to y, and this first x term is constant with respect to y. So the only y terms we have are the y, the xy over 10 to the 8th, and the minus, see, I did it again, minus 35 lambda y. Then we need the partial of L with respect to lambda. So x, y, and the xy, these are all constant terms with respect to lambda. So I take the derivative of, really, we're just getting the derivative out here, which is going to be a negative 38.5 minus 35 x minus 35 y, because lambda is the variable here, plus 1.6 million. We have this function that we're trying to optimize. So we're going to set our partial derivatives equal to 0 and solve. Notice that the partial with respect to lambda is just going to tell us what our constraint is. So no surprises there. In the first two equations, notice that we have a lambda in common, and that will give us a relationship between x and y. Once we have a relationship between x and y, we can use that in the third equation to find out a specific value of x or y. So one of the strategies that we're going to employ here is to use these first partials and find a relationship between x and y using lambda. We're going to use lambda to find a relationship between x and y. That is, eliminate lambda from the equations. And then once we have a relationship between x and y, we'll put that into our constraint to find a particular value of x or y. Then once we have x, we can go back and find y. Once we have x and y, we can answer any of the questions that we want to answer. Any questions? Yeah, so you would just eliminate the lambda from the first two. That will establish a relationship between x and y, and then use that relationship to plug into the constraint. Any questions? what we could do, so what we could do first of all is run out of space because great planning. So let's take 1.1 minus y over 10 to the 8th minus 38.5 lambda equals 0. And our other equation, 1 minus x over 10 to the 8th minus 35 lambda equals 0. So we just need to eliminate the lambda from these two equations. We can solve one of the equations for lambda and then substitute it into the other equation. So if we solve the second equation for lambda, then lambda is going to be, well, let's just do these things. We have, if we move the x and the 1 to the other side and then divide by the negative 35, so lambda is going to be 1/35 of 1 minus x over 10 to the 8th. And then we'll go put that into our y equation. Oops. 10 to the 8th minus 38.5 times our expression for lambda, which is going to be 1/35 of 1 minus . When I wrote this one, I thought to myself, I'm going to need more space than that. But the coffee didn't carry that message to the writing fast enough. So I'm like, nope, I already wrote it.
Professor, does it matter that it's x over 10 to the 8th minus 1, and then the last line it's 1 minus x 10 to the 8th?
So now we see this equation, with all, even with all its parentheses, is still just an equation in x and y. So I've got this constant 1.1 minus y over 10 to the 8th. We'll have minus 8.5 over 35. And then we'll multiply that by the 1. And then negative 38.5 over 35 times x over 10 to the 8th. So that'll become plus 38.5 over 35 times x over 10 to the 8th. My audio was off. Was there a question?
Yeah, I was just asking, does it matter? So the first equation that we did, second line, it's x over 10 to the 8th minus 1, and then the next line down, it's 1 minus x 10 to the 8th. Does that matter at all, or?
That's just me. When I moved the x, it became positive on the other side of the equation. 1 is negative 1, but then I divided by negative 35, and so I switched the order back.
Okay.
So if this is all being multiplied by negative 1/35, I'll just distribute the negative in and write it back in its original order.
Got it. Okay, thank you.
So here we have a relationship between x and y. It's messy, but it's messy, but that's what we got. I think the time for me to avoid 38.5 over 35 is kind of running out. But what we should note is that this is just a linear equation with x and y. So I've got, all right, 38.5 divided by 35. 1.1, how? Yeah, I should have seen that right away. That's all right. So we've got 1.1 minus y over 10 to the 8th minus 1.1 plus 1.1 times x over 10 to the 8th. All this is equal to 0. So the 1.1s drop out, and I'll have 1.1 times x, 1.1 over x. This number is called a 10, right? Yeah. 1.1 over 10 to the 8th times x is equal to 1 over 10 to the 8th times y. And so finally we arrive at 1.1x is equal to y. That took more effort than it should have, but I don't know if this is a more coffee problem or a less coffee problem, but I know what answer I'm going to apply. This first 1.1 came from our derivative. Our original objective function was 1.1x plus y, and so on. So when I took the partial derivative with respect to x, this 1.1 is where it showed up from the partial lambda with respect to x. And then 38.5 over 35 is 1.1. Because the 38.5 is just 35 and then 3.5. Which I didn't see because I guess it's early. Once we have the relationship between that 1.1x is equal to y, since I use the first two equations to eliminate lambda, now I've got to use my new combined equation with the third equation, which was just our constraints. So minus 38.5x minus 35y plus 1.6 million. Now I can take my 1.1x equals y and put it into my constraint. So negative 38.5x minus 35 times 1.1x and now we're down to a single value for x. Once we get down to the single value for x, we just have to work backwards. We can go back, plug that into our equation, our equation with x and y. Once we have x and y, if for some reason we need lambda, we need to know how the number of people changes. The value of p changes when we increase, when we change the lambda, or when we change the constant in the constraints. That's what lambda will tell us. Lambda will tell us how things are changing with respect to the constant in the constraints. So if we need to find lambda, we can go back and find lambda. Any questions? Comments? All right. This is just a process, what we need to practice. It's still based on taking the derivative, set it equal to 0, and solve. Take the results, plug them in the second derivative, and classify. In this case, we're not going to need to do that because we only got one value for x, and we can tell by the structure of the problem whether it's going to be a maximum or a minimum value. In this problem, rather than taking second derivatives, I would just take the x and y, plug it into the objective function, and then plug in values near x and y, and find out that that they'll be lower. And so that'll tell us that we have a maximum. When in doubt, look around. I think the more important thing that one of the frustrating things is that we'll tend to get lost in the process. This one worked out to a pretty simple system for us to solve, worked out to a linear system. So we're thankful for that. But one of the things that we should recognize about doing these kinds of problems is that when you're practicing these problems, it's less about, well, the way that we practice the problems, it kind of becomes about the process. And the process is not the thing that you have to learn. What we want, what's more important, I think, to focus on when we're thinking about these optimization problems is what we're trying to go after, what we're trying to say when we say that the gradient of f is equal to lambda times the gradient of g. What does this mean? What does it mean when we say gradient of f is equal to lambda times gradient of g? On the pure process level, we're just saying do this to solve the problem so that you can get points. But it's more important to understand what we're saying when we set up this first equation. What do we mean when we say the gradient of f is equal to lambda times the gradient of g? We're saying that the gradient of f and the gradient of g are pointing in the same direction. They might have different magnitudes, but if I make these two vectors equal, they'll be pointing in the same direction. That's the important part of the concepts. Then we take a step back and remember what the gradient represents. The gradient represents the direction of maximum increase. And so we're trying to find, and so we want the gradients to point in the direction of maximum increase to point in the same direction. And that means that the direction of no change points also in the same direction, because maximum increase is going to be perpendicular to no change at all. No change at all is tangent to contours. That means the rate of change in those directions is 0, because if you follow along a contour, the value of the function is not changing. When we think about it in those terms, it's less about memorizing this system of equations that you have to solve so that you could do that on a test, and remembering the concept that the gradients are supposed to point in the same direction, and then be able to write down what that means in terms of math. That means one vector is just a constant multiple or a scalar multiple of the other vector. So back in the day, when students were allowed to, I was giving in-class tests on paper, I started to allow students to bring note cards into the test. And a lot of students would write this down. And what I recognized was that the students weren't writing this down because it helped them remember, I want the gradients to point in the same direction. They're writing this down because this would trigger them to do this process. And I also noticed that in my algebra classes, students would write down m equals y2 minus y1 all over x2 minus x1, which told me on no uncertain terms that these students did not understand what the slope was. Because when you write things down like this, or write the slope formula down, it's not because you know the concept and you forget the formula. If you have to write down the equation, or what you consider a formula, or the slope, or the slope formula, you're doing that because you don't understand the concept. So that's when I really started reevaluating what we should be doing with tests, or at least what I want to be doing with tests. That's when I realized, hey, you know what? I think my tests might be BS, because I'm actually asking students to do this Lagrange multiplier stuff, and the evidence is suggesting that they are not understanding what the concept is or understanding why we're doing the things that we're doing. They're just doing what I told them to do, which is the worst result. Don't just do what the what someone tells you to do. You know what I mean? All right. So definitely practice this Lagrange process because your calculation foo needs to be very good, but don't forget what we're trying to do. I want to make those gradients line up in the same direction. Then I want you to think about why we want the gradients to point in the same direction. Any questions? Comments? Snide remarks? Remember, this week is mostly catch-up week, although the thing that we want to think about for the thing that's coming up next, I was trying to do this Marvel style. I wanted to get Mark Ruffalo in here to do a quick interview so he could spoil what's coming up next, but he wasn't available. So up next, I'm just gonna have to spoil it myself. In in this week, we want to remind ourselves about integration. And so what I want you thinking about when you think about integration is not stuff like parts and substitution and trigonometric substitution and all the other funky substitutions and the crazy parts tricks. That's not what we want to think about. I want you to think about integration is multiplication. But one of the factors is variable. And because integration is multiplication, but one of the factors is variable, integration is just addition. Integration is addition. So your evolution would look like 5 plus 5 plus 5 is just 3 times 5. All the terms were the same, so I can summarize with multiplication. Terms are same. When the terms are all the same, we get to use multiplication. That's what multiplication is for. It's for addition, but when all the terms are the same. But if I have, let's say, 4, 6, and 8, this is just an addition problem. The terms are not the same. So we need to use addition. Where integration comes into it is when instead of having a discrete sum, we have a continuous function. And we want to add up all the values of the function. Integration happens because we're trying to form a sum, but it's a sum, it's a continuous sum, not a discrete sum. Discrete sum is just the addition that we all know and love, a plus b. For a continuous sum, all of our terms, there's an infinite number of terms, and they're infinitely thin, and it's really weird. But the way that we frame integration is just to think about adding up values of continuous function. We take this continuous sum and we knock it back to a discrete sum that we can handle. We want to find the area under the curve. Area is just length times width, but our stupid length is all different values and it's changing continuously. So we knock it back to a discrete sum of areas that are just rectangles. So we can use length times width. We just need to take that concept and apply it to functions of more than one variable. But when you think about integration, we're just adding up values of the function. Integration is just adding up the values of the function. Subject to terms, conditions, quid pro quos, and so on. But the integral from a to b of f of x dx is the limit as n goes to infinity of the sum as I goes from 1 to n of f at xi times delta x. Length times width, add them all up, use an infinite number of rectangles. We model the continuous sum with a discrete sum, and we use our imagination to see where things are going. All right, that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day. Thanks for playing.